Hello everyone, today I will be discussing problems of Atcoder beginner contest 345. I will discuss problems from A to F in the reverse order, starting from the hardest problem first. And I will discuss until 5 minutes or until I am done with all the problems. So that will be done. Before we get started, can I confirm if audio and everything is fine? Okay, thanks everyone. I will start from problem F first. Problem F says colorful. Okay, probably I can start with problem A, B first until few more people join in the stream. So the idea plan would be A, B, F, E, D, C. Yeah, that would be the plan. First problem is left right arrow. You are given a string is consists of left bracket equal sign and right bracket. Determine whether S is a bidirectional arrow string. A string S is bidirectional arrow string if and only if there is an integer k such that S is concatenation of one left side arrow k equal to sign and one right side arrow. In this order with the length k plus 2. S is a string of length 300 inclusive consists of these three signs. Okay, my voice is breaking. Okay, let me just check if something is there. Is Anup from CodeChef in the chat? Ex CodeChef probably, but yeah. Okay, I forgot to switch the mic. Is voice better now? Hi Anup. Okay, okay, I will start from A again. A, B, F, E, D, C would be the plan. Left right arrow, you are given a string S consists of left arrow equal to and right arrow sign. Determine whether S is a bidirectional arrow string. A string S is bidirectional arrow string if and only if there is a positive integer k such that S is concatenation of left arrow k equal to signs and one right arrow in this order with the length k plus 2. We are given that S is a string of length 3 between 3 and 100 consists of these three characters. We have to print yes if the string S is a bidirectional arrow or otherwise no. We have some samples here. In this string, you can see the first character is this arrow, right character is this arrow, and then there are equal to signs in between. If you look at the second sample, then it's of type this. There is no left arrow, and that's the problem here. If you look at the third sample, there are two arrows in the right side, and there is no equal to sign, so that's also a problem here. So one way which I did was we can first look at the length of string, and then we can create an ideal string which we want over here, which would consist of one left arrow, then length minus two equal signs and one right arrow. And then we can check if the given string is equal to the older string or not. And that was essentially the solution for this problem. So what I did was I first took the string s as input, then I found the value of k, which would be length of s minus 2. Because if the length is 10, then there should be 8 equal to signs in between and the two arrow signs on the other side. Then I can create an ideal string. There can be multiple ways. Either you can run a for loop or something. What I did was I took this string and I know that I can create a string of equal to sign with k equal to and then a right arrow sign. And at last, if I am checking if t is the ideal string which I want is equal to given string, then I'm printing yes. Otherwise, I am printing no. And that was essentially the solution for this problem. There are many other ways to do this problem as well. You can first check if the first arrow is right arrow, second arrow is the the other arrow, and then all the characters in between are equal by running a for loop as well. And you can also maintain a flag or something. Like the code would be short in Python too. Like if you want to look at Python, what we can do is we can write the code as like that's how I will take the input. Then I can take value of s by len s minus 2, and then I can create an idle string like this. And I think the multiply by sign does the same job which I did over here. Like if you take a string and multiply it by k, I think it should create like a string like this of length k. And then you can also take the right arrow, and then you can at last check whether t was equal to s and print yes and no accordingly. So like that was pretty much the idea for the first problem. The next problem was integer division returns. Like you are given an x between minus 1e18 and 1e18 and inclusive. Print x by 10 where x is the seal division, where a denotes the smallest integer not less than equal to a. Like the one way, and like probably which does not involve a lot of casework, is like you start from x, and because we need a upper division, like for example, like what the problem is asking us is, so let's example we have been given 55. Then what happens when we divide 5 by 55 by 10? We get 5.5. So in this case, we should print 6 as the answer here. But for example, if we have 70, then 70 divided by 10 is 7. And the greatest integer which is greater than equal to 7 is 7 itself. So in case of 70, we should print 7. While for example, let's look at negative numbers as well. Like which example, minus 65 would be minus 6.5. And in this case, we should print minus 6 because minus 6 is greater than minus 6.5. Printing minus 7 would be a wrong answer here. And one way we can do is like we can start from x and we can check all the numbers x, x plus 1, x plus 2, x plus 3, up to x plus 9. Like we know that among 10 consecutive number, at least one number divides 10. So like that is one way to do it. And like that was what I did. And like this problem helps us catch a lot of bug because you should be aware of how integer divisions in different languages work. So like one way to do was take n as input, keep running a loop while you get a reminder when dividing by 10, and at last print n by 10. Like for example, someone in the chat is asking like a divided by 10, which generally gives us like floor division. So when a mod 10 not equal to 0, if we write, then we should get a one integer greater than 0, right? For example, like someone claims like this should also work here, right? Like this gives us the seal division. And if reminder is not equal to 0, then we should add plus 1 over here, right? The problem here is like this piece of code only works for positive integers. Like C++ has different, like it's floor division when you divide positive integers and seal division when you divide negative integers. So like this only works for positive integers. Works for positive integers. For negative integers, like if you have a code like this, like if a greater than equal to 0, print a by 10 plus a mod 10 not equal to 0, else a by 10. Like this piece of code would have worked. Like for example, like there are other ways to do find floor division as well. Like for example, when you want to find and and when you divide it by q, like some people like to do n plus q minus 1 by q as well. Like the essential idea is like you find you if you want to divide by 10, you add 9 to it and then divide it by 10 and take the floor division. Like this piece of code also only works for positive integers. Because for example in C, at least in C++, in Python it's always seal division. So like there are intricacies involved. Like for example, this piece of code would have worked fine in Python here, because Python it's always flow division over there. So like different, like the main reason why this problem existed over here was like so that you should be aware of how integer division works in different languages. Like in Python, it's floor division. In C++, for positive, it's floor, and for negative, it's seal. And like some people might also want to have would have tried like the idea of directly using the built-in function seal, like 10.0. Like this would have failed because like the for the larger integers, like there can be some round of errors as well. So like had the numbers be in range of 1 e9 or less, like this directly calling a seal function from math library would have worked. So like these were pretty much the reason why this problem was there, and this was the case. So like after problem B, I will move on to the later problems because like I do want to like cover the harder problems first. First, let's start. I will start with problem F, E, D, and C would be the idea, and like I would end the stream at around 7:55. And if something remains, like I would be available on Discord to discuss the problems. Like problem F says there is a simple graph with n vertices numbered from 1 to n and m edges numbered from 1 to m. The edge I connects vertex ui and vi. Each vertex has one lamp on it. Initially, all the lamps are off. Statement whether it is possible to turn exactly k lamps on by performing the following operations between 0 and m inclusive. Choose one edge. Let u and v be the endpoints of the edge. Toggle the state of lamps on u and v. That is, if the lamp is on, turn it off and vice versa. It is possible to turn if it is possible to turn exactly k lamps on, print a sequence of operation that achieves this state. And probably let's look at the samples first. Like in the first sample, the graph given to us is 1 2 1 3 2 4 3 5 and 1 5 1 5. And it says, is it possible to turn on 1 2 1 3 2 4 3 4? Is it possible to turn on 4 lamps here? And the solution claims yes, it is possible. The way to do it is like first we toggle the lamps on this side. So now green denotes like the lamps which are on. The second step, it claims like we should toggle the state on this edge. So like 5 will turn on and 3 will be off then. And then we should change the nodes on the edge 1 and 5. Okay, 1 second. Looks like I'm messing something. The solution claims like first we should switch the third edge, which is between 2 and 4. So like this would be the edge. And green denotes like the lamp on them is on right now. And like the not encircled in green denotes the length is not on there. Then we should toggle the state of fourth edge, which would be between 3 and 5. Now, if you see, like we have 4 lamps on right now. And then it says like we should also toggle the fifth edge, like which would be between 1 and 5. And here, if we toggle, like then if right now, if 3 was on, like now 3 is off here. And overall, you can see like there are 4 lamps on. So it is possible to print an yes over here. Like, and like if I move to the next sample says like, is it possible to turn on 5 lamps over here? And the answer is no. And it's important to see like why the answer is no here. Let's say like what are the possible cases when we change the flip the nodes of an edge right now. It can be case that like initially both U and V were off. In this case, after doing a toggle, like both of them becomes turned on and the number of turned on lamps increases by 2. If initially one of the node is on and the other is off, then once you flip it off, like it changes to U becomes off and V becomes green. Becomes a turn on. Like here, in case like U was on, V was off. After doing an operation on this edge, like lamp U is off and V is on right now. And overall, you see like there is no change over here. And if initially U and V were both on, then when now you do an operation on this edge, like both the lamps are off here. So the number of lamps decreases by 2. So like whenever you do an operation, the number of lamps can either increase by +2, remain constant, or -2. And initially you have no lamps on. So if you start from 0, like the only possible number of lamps you can have is 0, 2, 4, 6, 8, so on, something like that. So if k is odd, the answer is no here. And like that was one thing to notice. And that's why in the second sample, the answer is no when it asks us to turn on exactly 5 lamps. And like when let's look at the third sample as well, or probably like like one thing to notice here was it's nowhere mentioned that the given graph is connected here. It just says that given graph is simple graph. So like ideally, like taking an example of a connected graph. Mhm. I think I am back now. So like what I was saying was I was first taking an example of a connected graph. And warning, it says okay, I think I'm back now. Sorry. So like what I was doing was I was first taking an example of connected graph. Like let's say this is how a connected graph looks like. Then right now there are even number of nodes here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 nodes. And my idea was like if there are even number of nodes in a connected graph, then it is possible to turn on everything here. Like if I do an operation on this edge, I would be able to paint 2 nodes. And if I am able to, if I paint this edge, I would be able to paint 2 more nodes. If I paint this nodes, I would be able to add 2 more nodes over here. This will work like, and then probably I can toggle the nodes here again. And again, the idea was. So like overall, I would be toggling 3 times here. Like now when I paint this node, this will be turned off again. And like, in fact, a lot of like there are more problems which now if I paint the last edge, overall I would be making tabs 3 times here. If this like because it was even, I was able to do all of them. But let's say if a connected component has 5 nodes, then as we have seen earlier, If there are 5 nodes, then it would be possible to paint at max only 4 nodes. And like, and you, the way you can start by doing is like, this would be one way to do it. Like, although I have not formally explained the algorithm here, but like that was the idea. So like, if a connected component has, it's possible to paint everything. If a connected component has odd nodes, odd number of nodes, then one node will remain. And the way we can do is like, what we can do is like, we can run a DFS, like the, and at last we are returning whether the child node was painted here or not. For example, like when I'm running the DFS, let's say these are the sets of, these are the order of nodes I'm visiting. Like there would be more nodes, but let's say like these are the nodes where I am marking that some nodes as visited and everything over here. Then if you see, like I will start my DFS from this node, and first time I will move on this node, and like the loop ends over here. So I will return in the DFS called a boolean variable true, which denotes that this length is off right now. So like the parent nodes that this node is right now, this node is off here. And then I run a DFS on this subtree. I reach here, then I reach here, then I reach here. Now there is no other node in the subchild, so this says to its parent that it is off. Now the DFS comes over here again, and like there are no other nodes, so like it says to its parent it's off as well. And at that point of time, what parent can do is like, we can flip both the edges here. Both of these will be turned on now, and because the parent, like now once the parent knows that there are at least 2 childs which are off, what parent can do is like, parent can flip on the edge which connects both of these. So like when you do the first operation, the number of nodes becomes like this. Now when you flip on this edge, like the parent is toggled back to off state. And like this is how the structure would look like. Then like when you return from this side, it also says that this node is also off here. And let's extend this tree a bit here. Now when you move down this path, then like there are no other nodes, and when you come back, like this node also tells its parent that it's off here. At that point of time, like the parent can make flips on this and this edge, and both of them would be turned on right now. And now the DFS continues. Here, like here, this node will also tell its parent that it's off, and this will also tell its parent that this node is off. And then parent can flip on both of these edges to paint these nodes again. And like this way, if you see, like we are always increasing +2 nodes always. And as soon as we get k nodes, we stop painting the nodes again. And once this tree is done, like this also tells its parent that this node is off here. So like the parent can flip, like because the parent now notes 2 nodes here which are off, then parent can make flip on this edge and this edge to paint both of these. And the process continues. Like let's say there was no other node here. In that case, like there are odd number of nodes and parent root remains off. And like I will first check the code, like if I start routing from, if I take one of the nodes in each connected component and run a DFS on them, then I would be able to get everything there. Here I am doing something, and like let's first look at this part. Let's say like this for loop gives us all the connected components over here, where this vector GP denotes all the vertices which are in one single connected component here. Like I am here doing an inline DFS over here, like which takes one of the node as a root and starts by parent as -1. I also have a response vector here which returns all the edges where I should make flips here. And I also have a boolean vector to ensure that I do not run DFS from a particular node multiple times. Then if I am in the DFS part, Then if I already visited this node, then I return a false, which is a call to parent that you should ignore this node going forward. And then I mark a particular node as DFS as true, and I keep a tab on like the other edge, like if there is an unpaired edge over here, like a for loop. If it's parent, ignore it. Otherwise, run a DFS from child. If the child says returns a false, which means that the child is off or we should ignore it, then I should continue. Otherwise, I also maintain the index of the edge in my adjacency list. If you look at it here, I am taking input edges. All the nodes U, like adjacency list contains V and the edge index, and V contains U and the edge index here. Now, if I no longer need to print any more vertices, I simply ignore painting and just continue. Otherwise, like if the parent does not know any other child which is turned off, then parent takes a note of the other child which can potentially be flipped over here. So I mark this as the other node and continue. Otherwise, when I am here, like parent knows that OTH is the variable which is an edge index, which is the child is also off here, and the parent also knows that the current index edge is also off here. So in this case, like the parent can now flip the two nodes as we have seen in the example here. Like for example, if now if parent knows two such edges, if parent can do a flip operation on this node to ensure that the parent is still off but both the childs are on here. So I decrease the number of more nodes I need by 2. I add these two edges in the response vector I need, and I change this boolean variable again to -1, which is a node to parent that no, you don't know any other child right now which is not on right now. And when I am done with this loop, if the parent does not know any other child or there is no need to print any other node, then I return a true, which is a node to the current node's parent that the child is off right now. Otherwise, if I flip like the other node, like in this example, if there is only one node which if there is only one node which the parent node is off right now, then parent can now run a flip operation with itself and the node to paint itself, to turn on the lamp on itself as well and make a signal to its parent that it is on here. So that way I would be able to reduce the number of unpainted node required by 2. I add push the current that edge as input and I return a false here. And when I am done with all the connected components here, if there are still unpainted nodes, then I print no. Like otherwise I print yes and I print all the edge indexes I got. The question was, how do I find the connected components here? The shortcut, like the one way is like you can run a for loop from I to N, like you don't really need a DSU here, which I took in my code here. Like I slightly overcomplicated it by using a DSU, but we don't really need this once we have the vegetable. If you have already visited root, continue. Otherwise, now start DFS from this node. Like this will ensure that we run a DFS on all the nodes here. Here's the code. Like I don't really. Okay, 1 second. Like I stopped removing DSU. So like the complete code walkthrough is like I first take n m and k as input. Sorry. Like this would be the code without any compilation error. If it fails, I will run it locally once to see. Yes, it's running. The way to run is I first take nm and k's input. I maintain a adjacency list here. This contains two values like the other node and the index of the edge which it contains. If k is not print no, because we know that it's never possible to get odd number of nodes. Otherwise, I start from all the nodes. If I have already visited that node, I continue. Otherwise, I know that root is right now in one of the connected component which we have not visited yet. So I start a DFS from that node. And in the DFS, like there multiple edges can lead to a particular node. So if I reach an already visited node, I simply say that the parents should ignore this node by returning a false here. And otherwise, like when we should process this DFS, I mark visited as true. And the other index is the other index, probably one of the potential child which is right now off for the current node. Now I run a for loop on all the childrens. If it's parent, ignore it. Otherwise, run a DFS on child, and like the child says, you should ignore this node or the lamp is already on, you should ignore it. Otherwise, when you are here, like you know one potential edge index where the child is off right now. So if root knows one other child, then like now root can toggle both of these edges to turn these and these on while the parent still remains off. So like if we no longer need any node, ignore it. Otherwise, like the root, the parent does not know any other child which is off right now. Then the parent can keep a note of this child over here and continue. So like these were the other two cases. And when you are done with processing all the childrens, if the parent knows, like if you have to paint more nodes and if parent knows one of the child which is unpainted, now we can pick this edge to paint, turn on both of these nodes here. And like that is how you would be able to do it. And at last, if you still need some unprocessed nodes, then you print no like that, because our algorithm ensures that we take the maximum number of nodes as long as we do not reach the limit of k over here. Otherwise, print yes, print all the indexes which you have taken a note of. And yeah, that was essentially the solution. Any questions on this one before we move to problem E then? Okay, so someone in the chat was asking why I am not doing D1. Like I know one of the problem in today's code process round, which is D1F problem, because like that is the reuse from Satyam's contest of things cell round one. So and pretty much that was it. And हिंदी में समझाया करो भाई please. Like what I am doing is I am trying to learn English as well. Like if you know, like if you would be able to figure out some of the mistakes, and that is the reason why I am also doing this channel here. Like any questions on this problem before we move to problem E then? And looks like I won't be able to do C and D. So what I will do is at around 10, I will create one more stream where I will go through problem C and D and then call it a day. 10, 11, like whatever time I would be back. So like I will ensure that there is some explanation for C and D from my side. I don't think the editorial are out yet. So I will move to problem E then. Problem E says there are n balls lined up in a row. The ith ball from the left is of color Ci and value Vi. Okay, probably I would be able to do only one more problem. Like let's take a poll in the chat, like which problem do you want, C, D or E? And other two problem I will probably create a video and put it on YouTube. So like it would be before the end of the day today. Okay, looks like a lot of problem want problem D today. Then probably I think I would be able to do C and D today, both of them. So like let's go this way. First D. It says there is a grid of H rows and W columns, each cell having a side of 1, and we have n tiles. The ith tile is a rectangle of size AIBI. Determine whether it is possible to place the tiles on grid so that all the following conditions are satisfied. Every cell is covered by exactly one tile. It's fine to have unused tile. The tiles may be rotated or flipped when placed. However, each tile must align with the edges of the cell without extending outside the grid. The constraints are n is up to 7, h and w is up to 10, ai, bi is up to 10 here. And in this first example, like if you see, like these are the tiles which you have been given to you, and like in the 5x5 grid, here you place a 3x3 tile. Here you are placing 3 into 2 tile, and here you are placing 5 into 2 tile. So this works. And here you have rotated this tile, like it was 2 into 3 tile, but you are allowed to rotate here. So that's why the answer is yes. 1 comma 1 and 4 comma 4 tiles are unused here. While if you look at the second example, it says like you have 1 cross 2 tile and the only tile you have is of 2 cross 3. So if you place it, it will move outside, so it's not possible. In this example, like you have 2 cross 2 tile, but you have only one tile which is of 1 cross 1. So like it would be able to cover only one square here. So it's impossible. And in the third example, like the case is similar and it says the answer is no. Like, and like the way, how do I have approached this problem here? Like, where is my. So like the way I tried to do was like, let's say like let's first assume that there is some way to cover all the tiles here. Like let's just assume it for now. And let's say the way we have placed tiles here is, and let's say this was rotated here. I'm running out of colors here. Like let's assume that there is some way to paint all the tiles. And let's say like this is how the tiles are painted over here. Like say green is also rotated tile. While is not a rotated tile. Let's say pink is also rotated. Pink or like purple is color here. And what I will do over here is like I will start from this node. I will start from nodes in order and keep a track of tiles which I encountered for the first time. Like let's say I move on this tile in this order. And the nodes I have encountered here is first pink tile. Pink tile is when I am over here only. And then when I move further, I encounter a rotated yellow tile. Rotated like purplish, whatever this color. Let's call it orange tile. Then when I move further, like first I encounter a rotated green tile and a white tile here. Like I am ignoring duplicates which I encounter here. Like I don't really need them. Then a white tile. And when I move in the third row, like there is no new tile. Fourth row for the first to cell, no new tile. Then a purple, rotated purple and a pink tile. So what I essentially did was I think I repeated some colors, but let's assume like it is pink one and pink two. Like I ran out of colors here. So what I did was like I brute force on all of these order here and rotations. Like if I brute force on all the possible order which I can find when I move in this order and all the possible rotations, then you can see like because n is up to 7, there are 7 factorial possible orders and there are 2 to the power 7 distinct rotations here. So what I did was I rotated on all of this number of orders here and then I tried to fill nodes from the first cell. Whenever I encounter any empty cell, then I try to place the current tile which I need on that part over here. And if it leads to an outside the grid or if it leads to overlapping nodes, then I return that like this order is invalid over here. And like that was essentially the idea I had. Like now because I am brute forcing on all the order which I can encounter when I move in the edge like this, I don't have to try look at any other ways here. So like I have a solve function which takes all the permutations of nodes and then it calls a function try all rotations. If it says like there is one valid way, then this method returns true, otherwise this method returns false. And solve method, if it returns true, I print yes, otherwise I print no. Now I'm trying out all the rotations when the nodes, like the order of tiles I have is fixed over here. Like here again, it was a recursive function, or you can run a bitmask DP or whatever you want. The way I did it was like I maintained is possible boolean variable over here, and then I wrote a recursive solution, like which takes like current index which I need to process. It goes to the next node index without doing anything, and when it comes back, it toggles the tile again, and then it goes to the next index again. And when it returns back, it makes the current node again. Like the other way here would be to run a bitmask DP into like a mask from 0 to 2 to the power n, where the ith bit will denote like this node should be flipped, and if it's false, it should denote false. And now I have a try placing function which tries to place, like this is a method which takes a given order of nodes, like the final order which I need, and like the edges have also been flipped if required over here, and it should return a true if it's possible to place tiles here, otherwise no. So like I start with an everything empty, like no tile is placed anywhere, and then I start from index I, index j, like which is the order which I am running. If the current node has some tile placed on it, continue. Otherwise now I should place some tile starting from this corner here. So if I have ran out of tiles, I return false, like the tiles were not enough. Otherwise I take what is the height, like height of the current tile and what is the width of the current tile. And now I increment my index over here. Like there are two parallel for loops running, one for loop on all the tiles and one for loop on the order which I need. If after placing from this index, if I run out of a grid, then I return false. Like if I place the tile here, I would run out of a grid. Otherwise, I place this tile starting from this index. Like again, a for loop which runs on the rows I need, vertices I need. If it encounters a node which has already been placed some tiles, like it this denotes like there is some overlap over here, it will return false. Otherwise, it will place tiles here. And if I complete this for loop, then I know like for sure I have placed a tile on each node. No tile is going outside the grid because this ensures the grid path. Like I have not ran out of tiles as well, and like there were no overlaps, so I return a true over here. And like this was essentially the solution for this problem. It was more of an implementation heavy problem than anything else. Like I probably have 3 more minutes and I will go through problem C then. It says you are given a string S, find the number of string that can be resolved from performing the following operation exactly one. Let n be the length of S, choose a pair of integers I and j such that I is less than or equal to j and swap I and j characters of S. It can be proven that you can perform it under the constraints of this problem. So what this problem is essentially asking us is, like we have been given some string, let's call it a, b, a, c, A, A, D, D, E, F, G. Then we can pick any two index and we must swap once. And we have to find the number of distinct strings we can get. One thing to note is like if we swap two equal characters, the original string remains same. Whether we swap AA over here or we swap DD over here. That was one thing. And if we do not swap equal characters, then like we can iterate on like what would be the first character and what would be the second character. For example, like if we swap A and B, then the number of choices we have is this A, 4A, and like the B we have is only one. So there are 4 into 1 ways where we can swap A and B over here. Similarly, if we have to swap A and D, then the number of ways to swap A is 4 and the number of ways to swap D is 2. So there would be 8 different possible strings when we swap like A and D. Like if a character appears greater than equal to 2 times, it's possible to keep original string and let FA, FB, FC, FD, and so on is the frequency of all the characters. Then by combination, like the number of ways to swap A and B would be FA into FB. The number of ways to swap A and C would be FA into FC. Similarly, the number of ways to swap D and E would be FD into FE. So like we multiply all these frequency for all the 26 into 25 by 2 possible nodes over here, and we take some of these and add extra +1 if it's possible to maintain the original string. And like that was essentially the idea for this problem. So the idea was I maintain a frequency vector and like I count the answer, and I have maintained boolean a variable if it's possible to maintain the original string as well. So if there is a character with frequency greater than equal to 2, I say like it is possible to maintain the same string. And then I run on all the other loops to like take all the characters and take a product of all the two frequencies over it. So like this would be like taking the first character, the number of ways to pick the first character. This is number of ways to pick the second character. And when you multiply both of them, you get the number of ways to make swap between these two characters. Sum or all of these to get the final answer. And if it's possible to maintain original string, add answer plus plus. Like this was essentially the idea for this problem. So like probably I will put something for the problem E, like I record a video or something, and like probably it's around it. So thanks everyone for joining today. And like if something is unclear, like do join the Discord, like or put a comment in this video. I will try to answer that as well. So like that is the main plan.